I'd like to acknowledge my team member Yongjin Choi, who's the master technologist in the primary storage division, and he lead most of the current and previous machine learning projects in my group, and a lot of technical contributions is from him and his guidance for the team members. So today I would like to organize the talk around machine learning and generative model for SIPI. One thing I do want to stress is this is a unique journey that we went through for the past few years. And so we sort of, organized in looking in, a couple of topics within the machine learning AI area. For example, the neural network, we using neural network as a very powerful transformer to model things. And we are using principal component analysis for dimension reduction for a very complicated high dimension problem to a lower dimension vector problem. And some of the things that we cumulative for this kind of reduction, dimension reduction, is we were able to use what we call digital twins, which is the generative surrogate models, to model some of the complex high-speed channel analysis that we went through for both optimization and modeling. And finally, for the past year or so, we start to look into some of the true deep learning methodology where we are using generative adversary network that essentially we will try to replace the entire design process with machine learning. And as I mentioned before, this is a multi-year journey. We started roughly about 5 years ago, where we started with just a simple experiment with neural network for modeling purpose. And then we gradually, in the second year, we started using the principal component analysis to sort of speed up the optimization of a channel design. And then we move gradually into digital twin surrogate models, generative surrogate models in the following year. And then finally, last year, we start truly looking into using deep learning to substitute some of the design process in this particular case, simulation modeling design process. And so as you can see, the complexity of the problem that we try to use AI and machine learning to solve is getting increasing over time. And the overall goal is to use machine learning and machine learning and AI technique to eventually take over the majority of the engineering design process, so that basically it sort of can replace us with some of the expertise and the human needs to do the design. And we're trying to basically substitute that with machine learning and AI design process to minimize the human involvement and the expertise and training required to do these kind of design work. Now, I have to stress that this is a unique path that we choose because of the particular design challenges we have. And if you are dialed in and you're interested in this subject of machine learning AI, I presume that you are facing some of the problem that you want to design and model around using this technique. However, this is something that we think that it's highly depending on the problem and the nature of the problem you try to solve. So what I suggest here is what Hewlett Packard Enterprise itself went through in these past few years, because we have certain design challenges, and we decide to explore using machine learning AI technique to solve the particular problem. However, as your particular unique problem, you might end up finding a different path. But overall, what we want to share here is the machine learning AI technique that we use, and hopefully through some of these techniques, then you can also apply to a different set of problem you're trying to face, and you try to tackle the problem using the same technique, but rather than using the same problem, doing the same thing that we're dealing with, you might have a different problem, but you can use, hopefully you can take advantage of the technique and apply the method we went through and solve your particular problem. Now, the other thing important for this particular talk is because this is really only a 1 hour kind of fast presentation of our journey through this past few years. I'm not going to dig deep into the formula, the technical or the deep formulation derivatives and things like that of the problem itself, but rather some of these are published paper by us, and you can go into the reference in some of these things are in DesignCon papers and up and coming also papers. So those are the deep technical part and aspect of those things can be found in some of those reference. So rather, I would like to share with you some of the technique we use, some of the discovery and the result we have, and hopefully you'll find some inspiration to go ahead and solve your own problem also. So to start with the journey, we roll back to some of the early days when we start to use machine learning AI technique to solve some of the problem. At the beginning, what we just simply looking was a very simple problem, which is, can we use AI machine learning technique to model things that we conventionally use. So obviously, for SI problem, a lot of time we're using IBIS model or SPICE model. But the traditional design process start with basically the CAD tool supplier generate some kind of CAD tool, and then they give the component vendor those tools, and then component vendor would typically generate a reference model and give it to designer like us. And we do the simulation and we finish the design process, right? So now with machine learning, we start to look into, can we kind of modify this design flow and do something what we call self-correcting model. So in this case, what the CAD tool vendor is assumption is we provide some kind of AI machine learning tools, and the component vendor will train a machine learning tool model, which is typically is a neural network models for the designer. However, the new inspiration here is instead of just ending the process there, we can use those reference model to use test instruments to test against those those models. And so in other words, after we design, we can measure the result and see what how good the result correlates with actual simulation results. And if the same machine learning tool is provided by the CAD tool vendors, the test instruments should be able to measure the result. And then if the result doesn't match, you can actually retrain the neural network and correct the model itself. And we can actually even feedback to the component vendor, say, to improve the accuracy of the model. So the overall scheme is an example as follows, right? So assuming that we start out with an inaccurate IBIS model, for example, the red lines where that this is the original simulation model, and after measurements, we realize that the black lines are the actual measure result, and they don't match very well. So with neural network modeling, you can actually dynamically retrain the neural network model without knowing the underlying physics or the parameters, and you can just retrain the neural network to produce the correct result. And so this is basically the first year where we start getting involved in the basic machine learning premise is, okay, can we use the neural network as a modeling technique to replace for example, an IBIS AMI model or vector models? And the answer seems to suggest that yes, indeed, we can use neural network to generate these desirable simulation result. And the bonus for this particular technique is we can then basically use retraining process to get the desirable result corrected. So the lessons learned here, the important thing I want to emphasize is neural network is a very powerful transformer that can pretty much transform anything to any arbitrary output, and in this case a very complex IO model in this case. So now we move on to a more complex problem here. In typical design, we have a very high dimensional problem, and in this simplified example I want to share is where assuming you start out with a two-dimensional problem where the results are clustered as follow. And one technique you can use is to use some kind of transformation to center the solution space according to the mean solution, and then you can sort of start taking projections along a vector, and where you can project. You can pick an arbitrary vector in the two-dimensional space. You can project two components. One is the orthogonal component. One is along the arbitrary axis. The other one is perpendicular to the arbitrary axis, and then you can do all these projections of the entire solution space, and then you can sort of go through a maximization problem by rotating the arbitrary axis, so that basically the end result is the axis you pick have the maximum projection of all the result on that particular axis. So this is a typical mathematical eigenvector process to basically generate to maximize projections. Now, if you do that rotation, then you will find out that that particular axis in the two-dimensional space will have the maximum projection of the solutions. And then when you do a transformation and project that what we call principal component axis, you will find out that the solutions almost reduce to a one-dimensional problem with a slight perturbation at the secondary principal component axis. So in other words, what I've just shown you is a relatively simple mathematical way to project a two-dimensional solution space into a almost one-dimensional problems principal component axis. So indeed, that's how we start to look into and solve problem in the multi-dimensional space. So in the second year, what we have done is using this principal component analysis technique, and we start to look into how does it help us to do tuning of a complex SERDI. In this particular case, we look at a 56 gig PAM4 SERDI, and typically when you start to get involved in 56 gig PAM4 SERDI, you are dealing with about 20 to 30 tap variable, FIR filters, CTLE filter settings, and DFD tap settings, some of the gain, DC gain, offset, and so you end up having about 20, 30 linear dimension problems. And typically that become a very challenging tuning solution, because in real time, as the channel condition different, your SERDI algorithm has to basically converge to desirable solutions. And so what we have done here is we look into, can we look at the overall, given a particular solution range, like channel condition, varying loss, and or within the range of loss, within the range of crosstalk, for example, we collect all the optimized solution, and then we look into, can we use a principal component analysis to map the solution space into a lower dimension vector space. And so indeed, what we found out is, if we look at this particular example on the 50 PAM4, we can pretty much map the solution space into a 4-dimensional vector, principal component vector in here, and it will roughly contain up to about 91 or 92% of the solution. So in other words, we can actually map these 20, 30 dimension complex linear space into a 4-dimensional vectors, and significant dimension reduction on the region problem. Now, the key thing here I want to emphasize is, even in the reduced dimension vector space, the overall all the linear dimension are all participating in the tuning process. So in other words, each one of these 4 principal component vectors, these are linear combination of the individual linear components. So the tuning process is participated by all the tuning variables, even though they're in a reduced dimensional space. And one of the examples you can see in the top spinning cube is, you can sort of see, if we just project only 3 of the major component in the linear dimension, you can sort of see as it rotates, you can sort of see at some point in time, all the solutions sort of almost projected into in a linear plane. And so in other words, you can sort of see how a three-dimensional solution cluster can sort of map itself into a two-dimensional solution space. And that's exactly how we do this kind of complex dimension reduction in that sense. And so what is the advantage of that is essentially what we have found is if you use the linear dimension tuning, you will find out you roughly need about 20 tuning steps to achieve the desirable bit error rate result. And if we tune them in PCA vector space, you only need 5 steps to achieve the same bit error rate result. So in other words, if we tune in a reduced dimension PCA space, the solution can be achieved in a significant faster significant less tuning step to achieve the same desirable goal. So this is exactly what we have investigated in the second year, where we sort of map the complex tuning problem into a reduced dimension vector space. And by doing so, we achieve a faster tuning algorithm that can beat out the original linear tuning algorithm itself. So that's essentially is how we look at the problem. So okay, so in this case, the formulation of the problem is we start out with a design solutions space where we sample them, and we know that the original design, a complex design solution at that dimension, and where after which basically we try to use a principal component transformation where we take the eigenvector matrix and do a transpose and map that eigenvector matrix from a higher dimension original linear space into a complex linear combination of the original dimension lower in the lower dimensional vector, and then we remap the solutions into that lower dimension vector and try to model and do the optimization in that particular process. So in the third year, we start to look into what we call generative models and digital twins. And this is where the talk will be focused on the remaining time, because this is such an important concept, distinguish itself from the conventional classic discriminative model, where we're very familiar with. So here I need to give the definition of the discriminative model versus generative model. In the traditional discriminative model, where typically your SPICE simulation model or your IBIS simulation model are typically a discriminative model. So in discriminative model, what you're looking for is the conditional probability of an output given an input. So in other words, if I give you some kind of input, what does the output looks like, right? So this is a very classical the modeling technique. So for example, you have a lot of system configuration, you measure some of the performance, and then you go through the learning and modeling process. It could be a machine learning process and generate a neural network, or it could be even a modeling process to map into a IBIS model, or for example, or fit into a SPICE model, right? So then in a discriminative model case, what you would do is then, if you're presented with a new system configuration, and then you can interrogate the model, and then the model should be able to tell you what the expected output performance will look like. So this is a simple, input to output mapping. Neural network behave that way. Your SPICE model behave that way. Your IBIS model behave that way, right? I have an input. What does the output looks like? In a generative surrogate model, you go through the standard kind of sampling, just like the discriminative model. So you sample your configuration, you measure the performance, and then you start to build your model. However, in this case, in the generative model, you go through an additional Bayesian learning step, where the Bayesian learning engine will guide you to sample additional point within the overall solution space and sample the input point and then sample the output to generate the generative model. In this case, the generative model is no longer just look at what is a conditional output given a particular input, but rather the emphasis here is to look at the joint distribution between the input and the output solution space. So in other words, what is the maximum likelihood of an output given what is the maximum likelihood of an input distribution that will give a desirable output? And so under certain unique condition that you can actually sort of do this kind of reverse solution question where you say, if I have a desirable performance output, what is the maximum likelihood that a particular input setup will produce those kind of desirable outputs? So this is actually one of the unique property of the generative model on top of the overall C modeling of the joint solution distribution solution space of the system itself. So here I want to give an example of what Bayesian learning means. In here, I want to do a 1D demo of what Bayesian learning. Here, what in this particular example, what I try to do is I try to model this complex blue line arbitrary function with this kind of black, model solution based on some sampling, right? So in machine learning, there's always two competing process. One is what we call exploitation, which means that if you already sample some of the system, you want to use the knowledge you already gained, and you try to exploit some of the knowledge you already gained, and you try to improve your model, right? So this is what they call exploitation. However, there's a competing process, what we call exploration, where you really want to go into the system area where you have not sampled before, and you want to explore what the structure or the solution looks like over there, so you can learn something more about things outside what you already learned. So, but it's always a competing process in machine learning where do you want to exploit or do you want to explore? So here, what in Bayesian learning is we're using this acquisition function to guide us through the process to decide whether we want to do exploration or exploitation. In here, when we start with some kind of really lousy mathematical representation of the function, in here the acquisition functions will tell us, so, okay, maybe you should go to look into some of the outer area and do some kind of exploration. And so we sample the next point right here, and somewhat the approximation function somewhat improved, but still pretty far from the reality. In the next step, we use the acquisition function again here. After the acquisition function, look at the sampling point, and then it starts to suggest maybe you should do an exploitation. And as a result, we sample the area we already have sampled before, and we do another point, and we do another fitting, and then you can see the gray equations start to improve somewhat. And then in the next instance, again, you can see the acquisition function guide us to do exploitation, and another exploitation, another exploitation, and the function getting better and better. And at some point in time, now the acquisition function guide us to do, maybe you now should do an exploration. And so we sample outside our sampling area, and so on and so forth, continue doing this kind of exploration, and eventually we converge to a almost good fitting of the original function. So here I just want to share a simple demonstration of how Bayesian learning and to guide you through exploitation of a system to look at how the fitting will end up doing, right? So this is just a simple demo, but indeed that's how we do the Bayesian learning in a very high dimensional problem. And so that's essentially how we did it in some of the surrogate model we generate. So in here, what we have tried to do is we want to build a surrogate model of a channel. In this case, we have a 56-tick PAM4 SerDes, and it goes through a channel emulator where you can have variable loss parameters, so you can control to mimic different channel loss conditions. And we went through some of the sampling, and we sweep through some of the equalizer parameter like the CTLE parameters or DFE tap settings, and we sort of look at the response in the eye opening at different BERT steps, BERT 4, BERT 5, BERT 6, and then we sort of go through the mathematical fitting of all these different variable tap setting, and obviously one of the ways to reduce the sampling is to use the tap setting principal component analysis. And in this case, you can map it to a reduced dimension principal component and go through sampling of different all this reduced dimension space in about 5,000 sampling, and you can generate a surrogate model this way. And the overall shape of the fittings seems to be correlate with the measurements. And so now we can use sort of the reverse modeling technique where we can start saying under what tap settings we will produce the largest bit array differences, and so we can sort of sort out in priority what are the particular tap setting that can generate the most distinguishable output, and so the overall digital twins, well, how it works is we can sort of force the tap setting into a particular SERDE with an unknown channel condition. And then by doing that, we sort of observe what the resulting bit error rate is by measuring the SERDE performance and go back and so on back and forth. And if you do a couple of these force value and observe the BERT result according to the equation that we previously showed, then at some point in time, you can deduce what is a channel condition, after which basically you can sort of immediately dump the, optimal tap setting given that particular known channel condition that you already detected. And here, the unique thing about the digital twins process is the SERDE really doesn't need a smart algo to convert solution. In fact, what we did here is totally take over the SERDE tuning process and take over and deposit the right tap settings and look at the tap setting and look at the channel response. And by doing that, we deduce the channel response. And then by the digital twins, by optimization, can then force the correct tuning value into the channel, into the SERDE under the detected channel condition, and the optimization process can be completely done by the digital twin itself. Now, this is not just a limited to the, in this particular case, high-speed SERDE condition. We can actually have a lot of digital twins with the system digital twins and software digital twins, and these can be used for file system tuning, system dynamic system tuning itself. Now, so one of the things that in generative models, one of the things that record what we have done here is we have this high dimension original design space, and we went through this linear transformation of principal component analysis. We reduce it into principal component reduced dimension vector space, right? And one of the things that we can do is what we call autoencoder. Is we start with the high dimensional posterior, which is the in this example of the complex tuning circuits, and using the transformation, or in this case what we call encoder, we can map it to a latent space. In here it could be observable or unobservable latent space. In this particular case, in the principal component analysis, we map it into a observable principal component vector space. But in some cases, you can actually map it into a completely unobservable hidden space. I will mention that later. And once you into latent space, you can manipulate the latent space and output a desirable output through a decoding process. For example, here we can map it into eye opening, we can map it into a bathtub curve, we can map it to all kinds of different phenomenon based on the reduced dimension space. And this is what we call latent space. And so this is an overall very powerful technique into mapping a complex original complex solutions tuning space into a more reduced dimension a vector space, and then remap it into a desirable, maybe be that as a bathtub curve or eye opening and things like that. Now, remember, in this particular example, I mentioned the transformation is through principal component analysis, which is a linear transformation. And remember, in year one, we already said we can actually use a much more powerful neural network or multi-layer perceptron to actually map it into a highly nonlinear dimensional space. And then you can actually use in the latent reduced dimension latent space, you can map it back out to, again, use the multi-layer perceptron to generate a highly complex and nonlinear solution output, right? So in other words, in the current digital twins example, we have a linear transformation, but in the next phase of the investigation, we can actually use the multi-layer perceptron, which is neural network, to actually do this kind of highly nonlinear transformation. And so that leads into the third area of generative models. In here, I'm using a very conventional, I believe Google started up this kind of definition of a generative model, in which case they first split into whether you're explicit density or implicit density. In the explicit density means that the function is well defined, and then the implicit density is arbitrary, but that you use some kind of process to deduce after the observation. And so here I want to focus on two of the particular generative model. One is what we call variational autoencoder, and the second one is what we call the GAN, which is generative adversary network. And so let's look at some of the variation and autoencoder case, because this is very close to related to the previous example I mentioned. Again, here we start out with a very high dimensional posterior, which is observable space, and through a nonlinear, most likely neural network encoder, we can sort of map it into a distribution space, reduced dimension distribution space, where then you use the decoder to map it back out to a posterior, which is your desirable solutions. And here, the particular case, we instead of using a explicit function, we can have a Gaussian distribution in one of those example we use to describe to provide a generative solution. And one of the reason, here's what I can show you, is one of the example of a visual example of how kind of distribution solution different from a formulation solution. So here, the example I give you is it is actually an image from Impressionist painter Surrogate, and here these two particular painting, one is called, I think, Parade Dessert, which is the upper thing there on the Sunday at the park. But overall, the image here is constructed not by explicitly painting in a particular color, but rather you have these dots of primary color where the different density of them, the combination of these distribution of dots will form an image that you perceive a certain color. And similar thing in the Sunday in the park, same, where the image is actually constructed by a different density of some colors, dots. And so as such, you can actually construct a solution space based on distribution of certain functions. In here, these are strong color dots, and by having different density of color dots in different location, you form a perception of image here. And this is exactly one of the powerful solution of the generative solution, because now instead of looking for a particular solution, you are looking at the overall distribution in the latent space, where it can describe the entire the generative model, where the entire solution space is being modeled. as a distribution and center of a Gaussian distribution function or some kind of distribution function. And that is fundamentally the nature of the generative model itself, where you can start by a limited posterior observation, and you can map it into latent space where the distribution function itself can model the entire solution space. And that's where the generative nature of the solution comes in. And so the second technique that we look into of generative model is what we call GAN engine, which is a generative adversary network. Now, in the previous case, you are still dealing with having to map something from posterior to latent with some kind of explicit knowledge. In this case, we are starting to say, what if we are totally depending on using deep learning to model things? So here, instead of generative model that generate a solution, we are trying to use actually two competing AI engine. One is a original naive generator that basically just try to randomly generate some fake answer to the solution. But then we train a discriminator AI engine that can tell whether the generator is generating something fake or real, and then being able to tell it. And then you improve your generator by try to fake out the engines so that the discriminator cannot tell the difference. And so you can play the cat and mouse game, so that basically eventually your overall goal is to have they play against each other until the point where the discriminator cannot tell the difference between the real and fake image. So, and that's indeed how the generative adversary network looks like. You start off with a too lousy engine. One is the discriminator engine. If you give it a real image and versus some kind of fake image that the lousy generator generate, it really cannot tell the difference between whether that the image is fake or real, even though the image is very lousy. And so the first thing you do is to train the discriminator to tell the difference between a fake image and real image. Here, what you want to do is what in the objective function and loss function is to maximize the ability of the discriminator to tell, given a real image, it maximizes its capability to having a high score. Here, if the assumption here, if the image is real, then the score should be very high, close to 1. If the image is fake, the score should be very low, close to 0. So here, obviously for the discriminator, it should have two objectives. One is to maximize when you are given a real image, it can actually tell maximize the image to be as high a score as possible. By the same token, if you have a generated fake image, it try to make it as small, as close to 0 as possible, and thereby 1 minus it to be as high as possible. So this become a maximization function to optimize for the discriminator. So naturally, because we're talking about a competing process where the first discriminator AI engine try to maximize the score. So naturally, you will think that for the generator is to minimize the score for that particular function, so that basically you minimize in this case this particular case, because the generator only involved in this particular iteration, you would just try to minimize this particular case, which is basically you want to make the particular case to minimize the overall score of this function, where the discriminator can be able to detect a fake image, right? But in reality, what happened here is because obviously when you start the training, your generator is a very lousy generator, and the discriminator can easily pick out the fake image, and the score will stay relatively high. So you're really going to have a hard time converting the solution. But rather here, we kind of flip the problem around and say we want to maximize the ability for the generator to generate a fake image, to maximize the error that the discriminator will produce, so that you can mistaken the fake image as a real one. So it's a slightly different uh, loss equation to tune the solution. So in here, in the first iteration, we maximize the effect that so the generator output can so that the discriminator cannot distinguish between a fake image and the good image. So you can see the generator sort of improve itself in the image. Now, obviously in a subsequent process, the discriminator will try to improve itself once again, so that now the social generated fake image can be improved. Now the discriminator can tell the difference between a fake image and a good image. And again, you try to improve the generator so that now the discriminator cannot tell the difference. And so at some more time after this cat and mouse game, you achieve a solution where the discriminator can no longer tell the difference between a fake image that the generator generate versus the real image that was supplied in the training. Something that I think a lot you will probably have a lot of experience with what we call deep fake, right? So here in the example, you start with, like, let's say you want to generate a fake Mona Lisa image by a Van Gogh style painting or Picasso style painting, and through the competing training generator and discriminator, and same process as described before, you can see based on the trained result, you can sometimes generate a fake Van Gogh style paint Mona Lisa, or fake Picasso style image. So now what we turn the table around and say, instead of using this kind of image one-upmanship, I encoded the input waveform into some kind of image, and then I show the GAN engine what the output eye diagram looks like. And if I present enough of these input image versus the output eye diagram, and if I'm successfully train a 30 GAN engine, at some point in time after it converge, I can actually present an unseen channel condition to the GAN engine. It should, in theory, present me the correct eye diagram of the channel itself. And so, indeed, that's exactly what we did here. So here we have varying channel condition. For each channel condition, we generate what we call gradient angular field, which is the image that stress the spatial correlation between individual measurements of input waveform. And once the GAN engine read in those image, we can actually present with it different equalization setting. And here we have two different equalizer. One's the high gain equalizer, one is low gain equalizer, and the top row essentially are GAN engine output, and the bottom are actually actual measurement eye diagram. These are actual scope measurements. These are actual eye diagram plot out from the 30 eye diagram solution space. And so we can see for the converge GAN engine, the output of the GAN engine almost is indistinguishable from measured result. And so this is a converged GAN engine result. So notice here that the GAN engine have no knowledge of what equalization or high-speed 30 means. All it does is I'm presented with a input image, I'm presented with an output image. How can I train an fake output image that under the condition that the discriminator cannot distinguish? tell the difference between the real and fake one. So here there's no physics, there's no circuit and concept. This is just pure deep learning, using a deep learning process to enforce reinforced learning, where the discriminator and again the generator play this kind of one up min-max games to one up each other until the point where the output is indistinguishable from the input itself. Now, this is actually a illustration of how we can do it in SERDI, which is the electrical modeling. There's no reason why we cannot do the same thing on more, on a multi-physics environment where, for example, this one of the example that's being actively investigated right now is can we convert back and forth between a thermal image of a package versus the dipole distribution. So maybe given a particular dipole density, can we map out the thermal result, or the vice versa, given a thermal, can we integrate the power distribution density given a particular thermal distribution? So these are pure image to image correlations, and that's a perfect candidate for GAN engine. And the same thing for example here, where we map a electrical input to maybe an optical output of an eye diagram. And again, these are multi-physics. Again, the underlying physics, the GAN engine really doesn't care. More the important is, like, if you capture enough samples, then in theory, if the GAN engine converge, you can then take care of the physics through the latent space. So the important thing here, remember I said, in the latent space or the bottleneck in the autoencoder case is where these things are being modeled and handled correctly, with the physics. And so this is the reason why we believe this whole GAN technology holds a lot of promising future for not only electrical and electrical analysis, also multi-physics analyses. So to summarize, we think really has a great potential in SI. As we progress, we hope we can share with you that neural network itself is a very powerful transformation modeling tool. But if you couple that with generative model, where it covers not just the a one direction mapping, you look at the joint distribution between input and output solutions, and using the principal component analysis to solve some of the curves of dimensionality of these kind of generative models, you may be able to convert a very relatively complex model into through the into a machine learning AI modeling technique that can generate very complex solution in a relatively simple and lower dimension, reduced dimension problems. And autoencoder is one of the classic example. How do they do that? Where you funnel through a very high complex observable space into a lower dimension latent space, when you can manipulate your solution, map it back out into also a very complex high dimension problems. And in the last iteration, what we have shown is generative adversary network is really one of the first attempt we done to use the sort of reinforced learning, so that to take the modeling process out from human, but rather we use two AI engine to learn through deep learning the complex modeling technique that we require without very little human knowledge of the underlying problem itself, right? So overall, this is what we think. We share with you the past experience for the past few years. And I'd like to finally acknowledge a lot of these researchers through our research partner, CAML, which is stands for Center for Advanced Electronic through Machine Learning. It's a consortium, NSF-funded consortium with Georgia Tech, University of Illinois, Urbana-Champaign, and North Carolina State. And these are the member, industrial and member participating in the research. And a lot of these research I go through some of the researchers and students. And so I think this is all the presentation I have, and I would like to use the remaining time to answer any questions that anybody has. And hopefully, again, this is something that we share our own experience, and hopefully you will take the inspiration and search for a solution for your own problem. using some of the similar technique. And so that's it. Thank you.